Yes. This is the truly Australian form of finding out what something is. Remember how you find out what something is if you're an Australian?
You burn it on there?
Yeah, set it on fire and look at the light. This only works for metal ions, generally. You can't do this with other organic compounds. I mean, having said that, every element has its own elemental fingerprint. So you'd be aware that every element has different electron orbitals. Those electron orbitals are specific to that element. They're like a ladder. And when an electron is in the ground state at the lowest energy level, like in a cold gas, for example, hydrogen gas being an example, I guess, and then you won't see anything. But if you pass electricity through the hydrogen tube, it'll light up and it'll give off a colour. But of course, the human eye can only detect that one colour. What colour is this? Say it louder because you're right. Okay, I thought I heard rainbow.
Rainbow.
Mm.
Oh my god, I guess it was.
See, that's why one of these is useful. These mobile phone spectrometers. A little piece of cut up DVD that acts as something that divides the light. So I've got a camera on right now, yeah? Hopefully this works. See that?
Oh, it's a rainbow.
Yeah, you see, your eyes can't see that because your eyes aren't a spectrometer. But I'll tell you what, the world's actually a lot more beautiful than what we can see if you split the light up. Now that's these LED lights, but if I go out to this light here, which is a fluorescent tube full of gas, just give me a second.
Can anyone else see it?
Alright, this one's different.
Yeah, you're not going red and silver.
What do you see? See? Do you see a full continuous rainbow? No, you don't. You see lines. Those lines are the electron orbitals in the visible spectrum for the gas that's in those fluorescent tubes. LEDs work different to the gas. See, what you're doing is you're putting electricity across the gas, you're exciting the electrons up a couple of orbits, like a ladder, and then they drop back down, and they release a photon. And that photon is a specific colour. Your electrons can only go up specific energy levels and drop down specific energy levels relative to the specific element you're looking at, which is what's called the elemental fingerprint. This is why we can get starlight, and we can look at it and determine what elements are in a star. Now, I think that's pretty cool. You can do that. That's why space chemistry is a job. And at the moment, the rovers are testing out things on Mars. I think we're going to Venus soon. That's pretty exciting because that's massive high pressure with sulfuric acid clouds.
How the hell are they planning on doing that?
Oh, they'll send Matt Damon. How else are they going to do it? He'll be the first to find water and grow potatoes on Venus.
That's a super movie. Surely you watch
It was shit. I got about 5 minutes in and it stopped.
It's a good movie. No, you should watch it.
Matt Damon.
You should watch it.
It's got no, why not?
I feel like that's a good idea. Because it's got chemistry.
All right. Now I said you set it on fire, and you look at the light. In order to make electrons jump up energy levels, you have to provide them some energy. So you can do it with electricity, but in the case of atomic absorption spectroscopy, we do it with a gas flame. And you're exciting electrons up certain orbitals, and then they're going to drop back down and release light that's specific to those energy levels. Thing is though, That's atomic emission spectroscopy. And we're talking absorption. See, the tubes in that light there are emitting light because you can see it. Because there's electricity going across the tube. But that's emitting, isn't it? That's not absorbing. You see, the rungs on the ladder are the same for emission and for absorption. So what we're talking about is actually absorbing light of the same wavelength. Now, I'm not sure if I have the picture sitting in here. Blah, 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 blah. No, I need a comparison. See, teaching by Google Image Search is another fantastic resource. And these days it's ultra safe. Unless you open up that incognito tab, then you can look up anything and no dodgy stuff comes up, which I'm really pleased about. I wish to keep my job. Okay, emission, absorption spectrum. Oh yeah, one of this classic image here. Maybe this one. Alright, you need something that's going to split the light up, okay? Because otherwise all you see is a colour. And you know for a fact that that's not white now. You know that that's a full-blown rainbow. And that's only what we can see. How about in non-visible spectrums? Give me an example of absorbance that you've used that's in a non-visible spectrum. Say infrared.
Infrared.
Yeah, great answer, well done. Those are amazing. So here, hot gas, and you put it through a tube, then you get a continuous spectrum. This is hot gas in the, wait.
Hot gas.
These are not the drugs you're looking for. That's an incandescent light bulb. Okay, that's the one that vibrates the little piece of tungsten which has atoms vibrating at a bell curve range of different temperatures, which releases a continuous spectrum of light, including beyond and before the visible light in the spectrum. This is the two we're interested in. When you heat up a gas or pass electricity through it or provide energy to it, you get these lines, special colours, which relate only to the rungs of the element for that special spectral fingerprint for that element. Whereas if you pass the rainbow of light through the cold gas, the gas, what it does is it absorbs in the same locations. So that's where the light of the specific wavelength, such as red or this green, causes an electron to jump up and come back down from those energy levels. So it jumps up when it absorbs. So the emission and the absorption spectrum, they're one and the same. This is the one we're interested in for doing atomic absorption spectroscopy. Why am I looking at that? I'm going to go back to this slideshows. These are emission spectras. I've got these tubes. Maybe I could light them up for you after the talk. This is the colours that they release when you put electricity across them, but do you think they're one colour? As you're aware, they release different wavelengths. And these are the elemental emission fingerprints of hydrogen, helium, oxygen and neon. They would be the same as the absorption ones. What's that? That's what we see when we break apart the sun's light and look at all the Fraunhofer lines. Fraunhofer was the name of the bloke that discovered over 500 of those lines back in the 1700s. But that's pretty impressive. Okay, here's a very, very basic setup of a emission spectrometer. We're interested in the absorption spectrometer. Now, where is it? Yeah. Okay. There's a couple of key things that you need to know because you could get medium response questions about it. Like, there's no extended response anymore, that doesn't exist. Here is a lamp. It's a special kind of lamp. If you're looking for sodium, it's going to be a sodium lamp. If you're looking for cadmium, it's going to be a cadmium lamp. Because sodium releases the lines of colour, the wavelengths of light that sodium can absorb. No other elements absorb those specific wavelengths. Sometimes the wavelengths of one atom can be very close to another one. So it's about choosing the wavelength in the spectrum that's not close to anything else. That way, if you've got a sample that you're looking for sodium in and it's got the odd bit of zinc, it's not going to affect the concentration results. AAS is very, very good for very low concentrations, and that's really good when you're dealing with things like heavy metal poisoning, where a very slight amount can have a very big effect. So, let's say we're looking for sodium. You turn on the lamp, and you have the sample go up through the fire, the atomizer and the flame. And that just spreads out and makes sure all the metal ions are available, they're unbonded, and they're free to absorb light. So the first thing you start with is distilled water, and it will shine the light of the absorption. Now through the monochromator, what that means is it's going to just look at one of the wavelengths, monochroma, one colour, and then you've got this detector. Now when you put water through, it'll have all of the light go through and none of it's absorbed. And it's in a straight line. It's like a tight beam. And then you start to add the metal sample. And as you start adding the metal sample, it'll absorb some of the light, and instead of going to the detector through the monochromator, it starts to go off in random directions. And it's no longer detected, because it doesn't absorb the light and keep it. It absorbs it and immediately drops it back down and releases it again, but it's going to be releasing here all over the place instead of going to the detector. Sure, the odd photon will hit the detector, but an insufficient amount to register any credible difference.
So this is for absorption, so you get an absorption spectrum.
But we're only looking at one line of the absorption spectrum here. That's why we've got the monochromator. Now, the more metal ions there are, the more it will absorb. There's a direct correlation there. So the more concentration, the more it's going to absorb. There's another example down here. This one's the one we're interested in. Okay? Don't worry about that. I think I even got this from the old textbook anyway, so you probably won't even see it in your textbook. Does the machine make sense in a general way? Yes? Whatever. I don't know why I put that image there. That should be gone. That's inappropriate. I used to think I was funny. It's not funny. It's stupid. Okay.
What happened? Why did you stop printing the
Well, that was 9 years ago when I put that in there. Because it said inject, and like, you don't inject samples of a known concentration. You get the tiny little capillary tube and you drop it in there. I've actually done AAS. If you want to detect the concentration of something, like we do in a direct titration, you need something of a known concentration to be able to compare it to. So what you do is you prepare a bunch of samples of a very known concentration, maybe 5 parts per million, 10 parts per million, 15, 20, and so on. And you run that through the machine. So you start to get these points, concentration going up as you go. And they call it a concentration curve, but whenever you see it, it'll always be a linear trend line. And then you test your unknown sample, which will have some kind of absorbance. And you go, okay, there's the absorbance. We go across, and then you go straight down, and you've got the concentration. And there it is. Those questions don't relate. Now, I'm pretty sure I actually stuck some legit results in the OneDrive. Let's see if I actually did that. Volumetric analysis. SAT OOC NG results AAS calcium. So this is a non-test test. You guys are doing an infographic, but this mob at O'Loughlin, no, don't, what? Just download the thing. These guys, what they got was a set of results where I ran soft drinks through the atomic absorption spectrometer here at CDU, and I looked for sodium. So that was the concentration curve there. And that was based on samples which are made. Can I just look at the curve, please? Alright. Keep it down, peanut gallery. Do you know what a peanut gallery is? No. That's like from the 1980s, I think. Here. Not too bad, right? Some degree of random error about the line, but you see your coefficient of determination is 0.997. So it's, the closer that is to 1, the better you have a linear correlation. That's pretty much almost spot on. You might want to retest the 450 parts per million concentration, but the machine apparently can only go up to 400 parts per million for sodium anyway. There are limitations. When you look here, you can see 0.003298. That's a y-intercept. That means that you're not going through the origin of the graph. What should the absorbance be when you have distilled water? 0, that's right. This is telling us that we've got sodium present in a sample of distilled water. Is that possible? Yes, of course it is, in incredibly trace amounts. However, we make the assumption that it's not. So when you get an AAS question in the exam or in your test and you see dots about the line, that's example of random error. If you see it not go through the origin of the graph, that's an example of a systematic error. How can you fix it? You calibrate the machine, which means you drop all the data points down the sufficient amount to bring it in line with the origin of the graph. Tess? Yes, sorry. Oh, yeah, in physics and in chemistry, when it doesn't go through the origin, they're like, now what evidence do you have that there's a systematic error? And you go, well, it hasn't gone through the origin, look how smart I am, give me points. You know, that's kind of how it rolls.
Systematic errors. It's like when you go to NSC, it's like there's a systematic error.
Yeah.
It doesn't go through the origin.
Yep.
Genius.
That's the same thing. Or you could do like I did with my trick question and go, what evidence is there for systematic and random error? And there is none. And the answer is,
Was that the one in the practice test?
I can't remember. Now that I've done it, I'm not going to do it again, but
Because the one in the practice test, you can't see it in the graph if it's at origin or not, but the data set you gave us suggests that at
yeah,
origin.
I'm trying to teach. Alright, here, these are the absorbance. Close this crap. Nick Lenartzis is one of the smartest students I've taught. Well, no, smart is not necessarily the case. Like, he's just a hard worker and a natural in chemistry. He's a very intelligent man. This is the bloke that I used to let watch cricket in my physics lessons because he just did the work at home and ended up with an A+. So I'm like, you know what? Do whatever you want. It really spun out the relief teachers though, because they'd go into physics and start watching cricket and I'd lose it. And yeah, anyway, I always found that amusing. You can see here that for many of the stated concentrations, the amount of sodium that was present was actually greater. They had an hour to process these results. I just gave them the raw results. Now, do we have an example of the raw results? Yes, one here. What comes out of the machine itself is fairly simplistic. And you have to process this stuff quite manually. I would have liked to have done a assessment based on this, like for a PAC report, but I don't think it's really sufficiently good to get an A. So this is how the results come out. It does 3 readings. Now what do you notice here? 3 readings, milk 50%, sun-kissed alkaline spring water, standard 200 parts per million. Why do you think we run the standard solutions of different concentrations every 5 results?
Check if it's
Yeah. Those absorbances should be the same. If they're not, it can give you pause to guess, second guess the results you get. Other thing to note is it does 3 readings and they're all different. You average them. It's almost like a titration with the concordant values. This is a very powerful mechanism to get the concentrations of metal ions within a solution at very low concentrations themselves. The best thing you can do from here is to actually do the exam questions related to it. You may be hit up with the knowledge questions like, how come zinc contaminating the sample is not going to affect your ability to detect sodium? You have to answer why based on an absorption spectrum. And there's a few questions where they've compared the spectrums and they've said, which wavelength would you choose? And there'll be a bunch of wavelengths which are all close to each other, and then there'll be one in the element you want to find which is just sitting on its own. And you circle that one, and then you explain why. Oh, because it's not going to get interfered with by the other ones. As far as I'm concerned, these machines are generally quite accurate, so you can choose one that's close to others. But if you really want to rely on the results, choose one that's separate from all the others. It makes it better. Okay. Is that enough information on AAS? Well, I guess, how are you going to know that? I mean, until you get an A on the exam. Well, sorry, I think I asked a stupid question, that's all right. What I really should say is, did I make sense? Did I do all right? So, that is your revision on an AAS. I might do something else this lesson, but might also just go photocopy the... Did I do the revision questions for AAS for you yet from the guide? Because I don't think I have. Alright, I'm going to go get that for you and then you can do them. No, there aren't. I've got to get to that, and we're in the middle of recording till 1 p.m. today. And then I'm going camping on the weekend. I'm not going to do anything. So you're just going to have to wait a bit. Now, tests. You can sit the organic chem test. You can sit the analytical chem test in week 10 or week 1. Your choice. You can sit the organic chem retest anytime, probably I'd say up to about week 5, 6 next term. I need time to mark it amongst all the other stuff, because this retest stuff is all well and good, but it's also increasing my workload and I've got to fit it all in, most of the time in my own personal time, which I need to spend writing another analytical chem test for anyone who bombs it and wants another shot. So yeah, it's kind of flexible, but it's not going to go on forever. And also, if you don't arrange it yourself with me, it's not going to happen. It's not about me chasing you down and saying, hey, I bet you're not happy with your score. Let's see if you can get your true potential and have another crack. It's about you deciding that you don't accept that score and you want to represent your true understanding, in the knowledge that if you do worse, that's your score. But the problem with that situation is if you do far worse, either you've not studied properly or I've written an exam that's far too hard. So it's not supposed to go that way. Okay. When you are considering whether or not to do the retest, weigh it up. Remember, it can also depend on your other tests. If you get an A- and 2 A's, you're going to get an A. If you get an A and 2 A+, you're going to get an A+. The evidence is based on the whole portfolio, not on one test. And not just that, your percent score is not a grade. that chart that I've got on the wall that goes from score to percent is an indicative thing. There are people that have got less than what it says for an A+ on there, but when I look at the evidence, it's just a couple of silly mistakes. I'm going to put them in as an A+ anyway, because I reckon it'll get through moderation. We mark you via rubrics, which at the end of the day is pretty much your knowledge of what evidence is and where it sits on the rubric. A lot of that is gut feel. So don't think that your percent locks you into a grade. It depends on the evidence I see. It will also depend on the evidence of all 3 tests plus your infographic. This is why, and then it goes to moderation. And if I get someone who doesn't like what I do and the senior moderator decides that he doesn't like how I marked, it can all get changed. Nothing's guaranteed. All my marks held last year, but they were being extra specially nice because of COVID. I expect them all to hold again. And all teachers should be doing a thing called benchmarking, where they go online to this course and they get a bunch of examples from SAFEs and you have to mark them, and then you put in your grade and it tells you if you're way off or if you're on spot. And I've been on target every time. Doesn't mean I'm perfect, but it means that I'm pretty confident in my abilities. Right, rant ends. This is all available on your OneDrive. I hope you enjoyed your AAS.